I created a tiny URL for my talk, but I realized now that for people who walk in late, it's going to disappear. So let me write it down. There's a tiny URL. Oh, yeah? Okay, this is not super important. So yes, this is an R. Okay.
Game theory.
Cool. So let's start. So this is, thanks for coming back. This is part 2 of the tutorial, and I'm going to be talking about concave games. So the world is going to be very nice for this hour. The utility functions are going to be concave in a player's own actions. Equivalently, the loss functions of the players are going to be convex in their own actions. So just to remind you the thread of the whole tutorial, I'm going to be thinking about, in general, multiplayer games and simultaneous decisions made by these n players. Each player has their own loss function, or equivalently utility function. And the main question I'm going to be asking is, if they run a simple method like online gradient descent or variation of that, is their joint behavior going to get somewhere meaningful, maybe a Nash equilibrium, a correlated equilibrium, or some other interesting solution concept? Last hour, I made the distinction, the important distinction about whether the utilities are concave in one's own actions or not. As I was saying just now, I'm going to focus on concave games for this hour. In concave games, Nash equilibrium is intractable in general, unless the game is special. So I will mostly be focusing on either special games, like two-player zero-sum games, or solution concepts that are tractable in like correlated equilibria or minimizing regret. Okay, so this is our focus now. So in particular, I'm focusing on this left-hand side of the board. And I'm going to be discussing two questions. Is there a way to modify the training method, so add bells and whistles to gradient ascent, to remove this spiraling around and away from the equilibrium behavior that we saw even in very simple cases? Orthogonal question, oscillatory or not, I'm interested in what are the optimal rates via which online learning dynamics converge to equilibria. These are the two questions I want to talk about. Okay, so let's.
You close the microphone.
Oh, the battery is going. Thank you. All right, so as I was saying, these are very nice games, and we know a lot of things about them. So maybe the most fundamental theorem about these games is when the function that defines the payment of one player to the other player. So this is a two-player zero-sum setting. When it is convex and concave, and when the constraint sets are a product, so each player can choose from, player can choose from X, the other player can choose from Y. The players do not impose on the feasible actions available to each other. Then you have von Neumann's MinMax theorem. So the min-max equals to the max-min. So simultaneous and sequential are exactly the same things. The min-max optimal solutions are essentially unique, and they are unique if the function is strictly convex, strictly concave. And you've seen this picture. What you're trying to do is to find a saddle point, a global saddle point. These min-max points are equilibria of this game, where one player is paying the other LXY dollars. All right, so this theorem was proven by von Neumann about 100 years ago. In fact, von Neumann was inspired by a paper by Emile Borel exactly 100 years ago, who showed this theorem for, I believe, games with up to 4. So he was looking at games with 4 pure actions per player, and he was considering sets that are simplices over those 4 or 5 actions per player, and he established this theorem. He conjectures that the theorem is not true if players have more than 4 or 5 actions. So von Neumann disproved that conjecture, showing that this theorem is true generally. Yeah.
It's a historical question, out of curiosity, the way that, in the case that you remember, in the case that you have seen the paper of Borel, how did he try to prove the special case?
I don't remember. Yeah.
Okay.
Yeah. I haven't read it without that. All right. So other things we know about it is when your loss function is bilinear, like this one, and your constraint sets are polytopes. Computing minimax equilibrium is equivalent, polynomial time equivalent, to solving linear programs, which is the archetypical convex optimization problem. If your function is general convex concave, it's equivalent to convex programming. So there are intimate connections between optimization and minimax equilibrium computation. These problems are intimately related, as these results imply. Another interesting fact is that, von Neumann and Danzig were talking to each other when von Neumann was developing the theory of linear programming. During their discussion, von Neumann laid out a theory of strong linear programming duality. So when Danzig was writing his book, he had a construction trying to show this equivalence, but that construction was incomplete, and it was only recently completed, this computational equivalence between the two problems. That's another interesting historical fact. In any event, more connections with optimization came out of the literature of online learning and no-regret learning. So we know that if players of a zero-sum concave game, okay, so this function is convex concave. So if players of such a game each run their own no-regret learning method, such as multiplicative weights update or online gradient descent, their joint behavior will converge to equilibrium. But this convergence is in quotes, okay? So for the following reason, the convergence is really the one you see here. So it is convergence in the average sense. So it's convergence in the sense that the moon converges to the Earth. So the average of the trajectory goes to the min-max equilibrium, but it's not necessarily the case, and this is what's happening here, that the last iterate is converging to the equilibrium. In fact, the iterate very typically oscillates around and away from the equilibrium, or hits the boundary and oscillates around the boundary. And this is very typical of no-regret learning methods, such as gradient descent ascent, multiplicative weights update, follow the regularized leader, all these methods. And it's perfectly fine, right? So if all I'm trying to do is to compute the equilibrium from a perspective of a central planner who wants to understand what's going to happen in the game, that's perfectly fine. Maybe it's not fine if you view this online learning as a model of behavior of agents. So then it's not exactly clear if agents would use a method that oscillates around as opposed to kind of like identifying an equilibrium of the system. It may not be. It still could be. And the question is, can the oscillations be removed? So let's zoom into this picture that we have here. here's what's happening. This is our starting point. You get a gradient push, you go to this point. Okay. You get a gradient push, you go, and so on and so forth. And the point is that when you see spiraling around and away behavior, what's happening is really the momentum of this gradient descent ascent dynamics is wrong. It pushes you away from the target as opposed to towards the target, right? And the question is, are there ways to correct that momentum? And there are ways. So there are classical methods to do so. A few years back with Vasilis and Andrew and Zheng, we were thinking about GANs, and we decided we proposed this question, and we identified methods that are known to from classical methods that are known to exhibit this last iterate convergence. So here's one due to Popov, which is called optimistic gradient descent ascent. What this does is, without the pink is the classical gradient descent ascent dynamics. But what the pink does, it is undoing a little bit of yesterday's gradient, right? So at step t, at half the step size, I am undoing, and I'll explain why you may want to undo this in many ways. So, but you're undoing a little bit of yesterday's gradient. Similarly, the maximizing agent is undoing a little bit of yesterday's gradient. So in our picture, the effect of that is sort of like, rather than, for example, pushing down here to go further away from the target, you'll be adding negative of the yesterday's gradient to your current push. So ultimately, you may hope to correct the bad momentum that your dynamics has. So this is the pictorial. This is the picture of the idea. I'm going to show various explanations for why this works. Okay. This is the picture explanation. This is a proof by picture. I'm going to show you another two proofs. Okay. So this is the proof by picture that by undoing a little bit of yesterday's gradient, I may hope to correct the bad momentum and go closer as opposed to further away from the target. As I was saying, this method is classical. It was proposed by Popov 40 years ago. And there's an even older method, related one, by Korpelevich 25 years ago or so. So Popov is written here. Extra gradient is written here. And I'll explain what these two methods do by showing pictures. Okay, so these are the steps that happen in optimistic gradient descent ascent. So what I'm doing here is I'm representing the pair of points, the pair of iterates, xt and yt by zt for conciseness. And by f of z, I'm representing the gradient field, right? Which is gradient with respect to x minus gradient with respect to y, because one is trying to minimize and one is trying to maximize. This is the right thing to do. So what happens in OGDA is you do the following. So at the current iterate, you you compute your gradient field and consider that point. But you're also taking the difference between your current gradient field and the one at the previous iterate. And you do the joint push. So you travel to this point as opposed to this point. That gradient descent ascent would do. Now, why would you want to do this? This goes back to the question that Manolis asked me earlier. So Manolis said, okay, like if you're spiraling around and away from the equilibrium, wouldn't you want to run the steps backwards to go towards the equilibrium? That's called that has a name, right? So it's called the proximal point method, where that you can show works. Okay, so in the proximal point method, you want to push towards the gradient that you don't have. Okay, so at step t plus 1, you want to subtract your future gradient. Okay, so these are called implicit methods, because to run this, you have to solve a fixed point problem. to run this method, and it's expensive typically. So what OGDA tries to do is to approximate the gradient that you don't have with a current gradient. It's a first order approximation with a current gradient and the first derivative of the gradient. Right? And if you use this approximation in this method, you basically recover this method. So this is what OGDA is trying to do. It's trying to approximate this proximal point method. Make sense? There is a factor of 2 missing. Well, so what? What do you say?
Data. In the approximation.
No, so this is the approximation. You take this and plug it into here, so you get theta here. You need a net over 2. No big deal. Okay. Yeah. So you typically these methods actually are a bit slower compared to because you lose this at this factor of 2. All right. So what does extra gradient try to do? It's also an approximation to proximal point, a different one. So here you do the following. You're sitting at the current point. You compute your gradient. You go there, compute another gradient, and use that gradient here to travel to your next point. That's also an approximation to a proximal point, different one, where you now instead you say, look, I want to approximate this by just, in my head, doing an extra step, going there, seeing the gradient there, and using that now. Okay, so this is the approximation you do here. So this is the motivation for these methods. All right. So now, if you believe me that this corresponds to running the dynamics in the reverse order, thereby converging to equilibrium, and if you believe me that these guys are approximations to those backwards dynamics, then that's another proof of why you would hope these methods to converge, last iterate converge to equilibrium. So that's the second-hand wavy proof, okay, that I'll give you. Yeah, I mean, I don't know if this is folklore, but it was recently used in a paper by Mokhtari to analyze these methods and establish some rates of convergence. What was classically known is that these two methods, and that goes back to a question that Mike asked, what was known from classical results is asymptotic convergence, asymptotic last iterate convergence of these methods to the MinMax equilibrium, and also rates for the average of these two methods, the average iterate. So both these methods, we know results for the average iterate, also maybe the best iterate, and asymptotic only for the last iterate. Okay, so that's it, that's that. Average iterate means in the same sense that I mentioned earlier, like the average of the trajectory, like this object. This object versus this object. This is the difference I'm talking about. Yeah. So spiraling around the equilibrium satisfies that this converges to the equilibrium, but not that this converges to the equilibrium. All right, so I kind of like showed you a figure. I hand waved why this worked. I decided to give one proof in my whole tutorial, precise. So I want to show you why this has average iterate convergence with rates and also asymptotic, like a formal proof. Question?
Well, I was thinking that if you're far out, you just have to define potential function.
Yeah, will.
Okay.
Well, potential functions are very useful in optimization, but yeah, I will. Okay. All right. Before I do so, though, I mean, I'm sure I've shown you the methods in the unconstrained domain. Like, you can implement all the steps that I have in this picture. I wanted to also define them in the constrained domains. So the first thing I want to do is actually replace this method by this method, right? Which also has the form of like, getting this half step, right? And so, it's not hopefully, right? So this method has this half step explicitly, right? So this half step is this point here. So you go to that half step, right? So here and here, these two equations, At that half step, you compute your gradient, and then you go back to your original point, and you make that push, right? So you can similarly write this in that form. It's a little bit different, okay? So the gradients are always the same, but you make a step in this half time in the half interval, and also in the integral interval or whatever. But so this, I mean, if you sum this up, you will see that it recovers this dynamics. Now, once you write them in this way, you can define their projected version. So here's a projected version when my constraint set is a product constraint. So both, for every gradient step, you project to the constraint set for both layers. You do the same over here. Every gradient step, you just project to the constraint set. And if your constraints are coupled, you can do the same, right? I mean, you just write everything in terms of z, right? So you use this z, which is the pair of the variables. So you have now this very nice form. Okay, so okay, let me actually change it to any constraint set. So you do a half step. So you go to the previous half step. You take a gradient. You do gradient with respect to zt. You project to the constraints. Then you go back to this half point and interpolation point, and you do another gradient step with respect to the original gradient. An extra gradient is similar, like as shown in the picture. So these are the methods in the constraint set, constraint case. And these are all known to asymptotically converge to the min-max equilibrium. Okay, so now let's try to prove it. Can you read these letters? Kind of. So I wanted to fit it all in one slide, so that's why I wrote it small. All right, so I write down a potential. So here are the dynamics I'm reminding you, right? So like there's this interpolation point. So you have these interpolating points and the actual points, right? Again, you do a gradient step from interpolating point to the next interpolating point. And then you compute your real new iterate by going to that interpolating point and do another gradient step with respect to the original gradient. So I'm going to write this potential function down. What is this potential function? It's a time t and a tiny point z of my interest in my domain is just the sum across all time steps of the inner product between my gradient field and zi minus z. Okay. It's not clear why this is a good potential, but I'll show you that if you make this small, you are in good shape. Okay, so if you make this thing small, it's good. All right, but let's postpone that discussion for now. In fact, for the whole slide, I'm not going to use the fact that I'm in a good game. Like for the whole slide here, I'm not going to be making any use of the game being concave. All the computations I'll do here are generic. I'm only going to use that in the next slide. But so for now, in fact, I'm not even going to use the fact that this is a gradient or whatever. This is any map, any multivariate map. All right, so I wrote down this potential, and then the first step is kind of silly. I just take, I track the difference in my potential, which is exactly the last term of the sum, which is here. And then I take this last term of the sum and break it up into 3 terms, okay, which are written here. And I mean, what I did here is I subtracted this guy from here, and I have to correct that over here. And also, then this is another correction. Okay, so I didn't remove some stuff. These are the 3 interesting terms that I'm going to underline with different lines to keep track of them. Okay, so there's going to be colors here to help you parse the proof. So what I want to do is I want to bound this. Okay, and I want to bound it by bounding these 3 terms. Let's start with the, let's see, which one do I do? I think I do the last one or the middle one? The middle one. Is this the last one? The last one, yeah, the last one. You're right. I cannot, yeah. Anyway, so let's start with the last one. Okay. I'm a backwards guy, right? Okay, so like last one is this term. Now claim that from the definition of this update, you actually have this inequality that for any point z in your domain, this inner product is bounded by this. So let's try to see why this is true. I didn't prepare for the right picture here, so let's see. So I have this update. All right, so I guess there are two cases for this update. Either you do projection or you don't. Okay, if you don't do projection, this should be trivial because, there's going to be some equalities there. So let's do with projection. So with projection, what's happening is that kind of like that, this is the projection of this point. So, you have this point here, it's on the boundary because you did project this set S. You projected, what did you project? You projected this point. Well, this is not a good projection. It's projected this point. So what does it mean that this point is the projection of this point? It means that if you choose any other point, z, in your domain, this angle is, how do you say in English, obtuse. Okay, this angle here is obtuse. So which means that the difference of this guy and that inner product, this minus that, is negative for any z that you chose inside the domain. Okay, and if you rearrange that, I promise you will get this one. Okay, so you got that. Next step is to an equality. So as it turns out, this inner product, this is a very common trick people do. This inner product is actually the difference of a bunch of differences squared. Okay, so it's this minus that squared, minus this squared, minus this squared. This is a very common trick. Okay, so you get this one from there. By analyzing this middle term, you get an analogous statement. And now I'm going to do some color coding to help you. So the purple term is the difference of the interpolated points in one step. It appears here with a negative sign, here with a plus sign. This is the difference of your arbitrary point that you chose here, this point here, with the two interpolated points, different ones, but these terms are going to survive together till the end. And then you have the red one, which is the difference of the next interpolated and ZT, and ZT and the previous interpolated point, interpolation point. Okay, so these are the two things you can write. I mean, I don't know how much you can parse out of this. I mean, it's going to be an algebraic manipulation. So I don't, I'm not going to offer you. I offered you two pieces of intuitive evidence. Now I'm going to do some algebra. Okay, so you have this and you have that. And now you have to analyze this inner product. So for this inner product, you're first going to do Cauchy-Schwarz. And also, remember, this is the only thing I'm going to use in this slide about this F. That F is Lipschitz, is lambda Lipschitz, which came from the fact that what I'm thinking about is a smooth problem. Yeah. So I do Cauchy-Schwarz, and I have basically this difference, L to norm, and that difference, L to norm, and L is coming from the Lipschitzness. And okay, so I do here some triangle inequality, replacing this difference with these two distances, and then I'm gonna be applying Young's inequality to upper bound, various products with a bunch of quadratics, and trying to recover differences squared that appear upstairs, because I want to add them up and cancel things out. Algebraic manipulations and details don't really matter. The signs are important, right? So it's important that this cancels that. These guys are going to survive. And then what you want is that this -1/2 is going to try to kill this guy, this other red thing. And this -1/2 is going to try to kill this guy. Okay, so if you try to implement that strategy and you add these 3 inequalities, what you get is this nice thing that my potential function in one step can be upper bounded by something with a negative sign. Right, and a coefficient. Hopefully, I'm going to set the step size so that this is actually positive. So this whole thing is negative. Another thing with a negative sign, this difference that I claimed from the beginning that is going to survive, and this difference here. So, and my plan is to telescope this one and to telescope that one. Okay, so telescoping everything, details don't matter. I arrive at an upper bound for my potential at step t, where I've just summed up this. I summed up that. I exploit the fact that these are consecutive differences of the same object, so I telescope it, and similarly for that. So, long story short, if you also initialize that the first interpolated point is equal to the starting point, you get a nice upper bound of your potential function written here, which is a bunch of negative stuff. The difference of the arbitrary point z and the first interpolated point, z and the current interpolated point, and this negative term. So effectively, you have a bunch of negative terms, and just this difference between your arbitrary z and the original interpolated point, and your arbitrary z with the current interpolated point. These are the important features of this, right? A bunch of negative stuff, and this is the only interesting piece of information on the right-hand side. Good, so I copied it here. So now we're ready to actually prove average case convergence. Okay, so again, there's not much intuition you can get out of here, except that, yeah, what I want to get is I want to bound each of them with differences of differences squared, and I want similar terms to appear so that I cancel things out, and I have a bunch of negative terms on the right-hand side. So that is going to be my handle. So how do you show, after you have that, how do you show average case convergence of optimistic gradient, average case of optimistic gradient? Well, the first thing to do is to make sure that these things are actually positive, so that these are actually negative terms. So this is what's done here. If you set your step size to be 1 over your smoothness, which is the right constant, you get that all of these guys are negative. So the only thing you're left with is non-negative, is this thing on the right-hand side. So for any z you plug in, then the maximum that this potential function can get is the maximum that the single positive term on the right-hand side can get, which is the radius of your constraint set in this, L2 squared. And this is the notion of radius of your constraint set. Right, and that's it. So you get that, the normalized, the maximum over points in your set of the normalized potential function divided by t is upper bounded by something that depends on the size of your constraint set over t. That's the important thing, that as you grow t, that it gets smaller and smaller and smaller and smaller as much as you want. And now the question is, why is that a good potential to have, right? And okay, so let me now unpack why this is good. So now I'm going to remind myself what f is. So far I haven't used it. I only use that it's Lipschitz. I remember that f is my gradient field, right? So minus gradient with respect to x, so plus gradient with respect to x, minus with respect to y. And I'm going to remember that this L here is convex concave. Again, this is the first time I'm going to use it. All right, so now I'm going to use the fact that my potential is as small as I want it to be, my average potential is as small as I want it to be, together with two facts to argue that I'm close to a minimax point. So how do I get that? Well, you know, this is just the definition of this. This is the definition of my potential. This is normalized. So I didn't do much here. I'm just using the fact that this thing is smaller than this thing. Now I'm unpacking it, replacing F with what it is. So it's that's an equality. And then I'm going to use convexity of L with respect to X and concavity of L with respect to Y to lower bound this by this and upper bound this by this. So, you know, so you get some cancellations here. This term and that term cancel out. So I get the average over times of, right? So X is an arbitrary, X, Y is an arbitrary point of my X iterate against that Y, my Y iterate against that X. And that's basically the duality gap. So if I do Jensen again, I get that the loss at the average X against this arbitrary Y minus the loss of an arbitrary X against the average Y is upper bounded by this quantity that I can drive to as small as I want it to be. And that's it. Okay, so you bound the duality gap by whatever you want, and that thing drops like 1/t. As long as you set your learning rate to be something over the smoothness. This is the whole proof for the average case convergence, right? So ultimately, what I get here is the average points. All right, so that's the proof of the average case. Yeah. So I have here the asymptotic one as well. I'm not sure I wanted to spend too much time on it, but let's wave some hands. I'm not going to do last iterate goes to the point rather than just the average.
In the limit.
Excuse me?
In the limit or not in the
In the limit. Okay, so let's see what do I do here. So I now pick Z star to be an arbitrary minimax solution. And okay, so I guess I'll do a few things. Okay, so remember when I was telescoping before from t down to 0? Here I'm only telescoping between some little tau and some big tau. So that's again telescoping a bunch of negative terms. And now, you know, these blue terms are not from t equals 0, right? This is a tau, right, where I started my telescoping. So that's the important thing there. Second important thing is that I'm taking Z star to be a minimax solution. By the previous analysis, if I plug in to this difference of my potential, Z star, of course, this is a quality. All the terms that are here and not here. This is the sum from t tau plus 1 to t, the inner product. So that's just the quality. And now by the previous analysis, but because Z star is an equilibrium, you know, this is lower bounded by 0. So that the duality gap is 0 at the Z star point. So I get this inequality, which, long story short, because this is bigger than 0, I can plug it in here to get that this whole quantity there is non-negative. So this is this. I rearrange this to have that my equilibrium against the interpolating point at time t is upper bounded by my equilibrium at the interpolated point earlier in my iterations, this positive term and a bunch of negative terms. And here's now the observation, right, that these sums keep, like, as t goes to infinity, I keep adding negative stuff. But, you know, because my domain is bounded, these terms cannot go as, like, if I take all of these terms to the right hand, to the left hand side, they cannot also be becoming smaller and smaller. So it must be the case that these sequences go to 0, because if they don't, I will be adding stuff to the right hand side. The right hand side is going to be becoming smaller and smaller and smaller. Well, these guys, there's only a finite amount they can, you know, go down. So these sequences must actually go to 0. Okay, and that doesn't mean that the sequence necessarily, it's not obvious that this implies that the sequence converges. But okay, if you do another 3 lines that I want to do, because it's going to get too heavy. This is trivial steps, but the sequence does converge to the Z star equilibrium. Okay, so I have posted these slides. You can study the last few steps. So again, this does not imply that the sequence converges, but you can actually do a little more thinking to show that it does converge to the Z star equilibrium. Was that the question? No. Any other questions about this? This went a bit fast, but again, all the details are on the 3 slides that are presented. It's not like a more exotic argument. It's like some algebraic manipulations, clever algebraic manipulations to get an upper bound on your potential function, and then you do some extra work.
So this is general for variational inequalities. There really is a bigger framework here.
Yeah.
In fact, it might be helpful to comment. The proximal point method is really what's here. The rest of this is numerical, kind of a discretization of that particular method. So would you really sort of say the proximal point method is a good method for solving quickly classical problems?
That's right.
And your formula is a variational inequality and kind of stuff that all up. The proximal point method was developed for optimization, some generality factorization.
Yeah. Right.
So you might, it's an intuition comment, but your whole setup here was for oscillation in MinMax problems. Why is proximal point good for that? Because the rest of it is just numerics, the OGDA or the extra variable, which are particularly integrated.
Right. So I guess the intuition for that is that it goes backwards. Like it does this paralleling away and around and away, it does it backwards. Now, analyzing the proximal point, you still have to analyze it to show that it actually does do that. Right?
Yeah.
Oh, yeah, sorry. The question, so Mike asked, could you provide some intuition about, I mean, I said earlier that this is trying to approximate the proximal point method. Could you provide intuition about why the proximal point method, does the job you want it to do? And I guess so my answer was that intuitively, the proximal point method tries to do the iterations backwards in time with this implicit update that it has. But yeah, like showing it, you still have to do some algebra to show that it does. So yeah, so I decided to present the algebra for a method that actually is not implicit, but yeah, that's right. Yeah, I don't have, honestly, too much more intuition to provide. Yeah.
You know the last iterate rate for proximal point?
I'll get to that. Yeah. Oh, so Yang asked, do I know the rates? So this argument shows asymptotic convergence of ODBA to the MinMax solution. Do I know rates? I'll talk about that in the next slide, actually. So, okay, so classical work establishes average convergence rates for these methods and other related methods. And asymptotic convergence results without rates, or with like not effective rates. In the case, again, that my function is convex in K. What do I know about rates? There has been a lot of there's an explosion of recent work trying to figure out the rates of last iterative convergence. Most of that work has studied the unconstrained setting. So we understand very well the rates for the unconstrained setting. So for the constrained setting, we have bounds, but they're not, I mean, you can already recover some bounds from these early works, but they're not effective in the sense that their dimension dependence is not good. Okay, so the time dependence is good, but then in front of that, there is a bad dependence on the dimension. So one open question that is interesting to think about is, in the constraint setting, getting algorithms or showing that these two algorithms converge with a rate that is polynomial in dimension and the iterations that you make. So that's a very interesting question that I didn't know the answer to until maybe like 40 minutes ago, when Yang Chai told me that they have an analysis of the extra gradient method. with this dependence. Now, what I told Yang is that he shouldn't announce it until the end of the program so that we show that something cool happened at time. Okay, but let's say that there are partial answers to this question. Another thing we know, and I think this was a paper, this was shown in this paper and that paper. With now Golovich, Patel, and Azure, is that the last iterative convergence rate for this method is going to be slower in terms of time compared to the average rates. So the average rate showed you for this method was 1/t for the average. The last iteration is going to definitely be slower than 1/√t. And I believe this is what Yang showed in his paper. So for this method, it is indeed 1/√t times some mild dependence on the smoothness and animation. I don't know if you want to specify more.
I think that's it.
Okay, all right. Let me move on to multiplayer games for like the last 10 minutes of this presentation. Again, I'm still in the nice, I'm still thinking about nice games. So utility functions are all concave in one's own utilities. Loss functions are convex in one's own actions. And okay, so what do we know about this game? So a comment I made earlier is that Nash equilibria are intractable. But the new comment I want to make here is that correlated equilibria are tractable in under very general conditions. And I wanted to illustrate this result by Papayomitou, Ralph Garden, and Jiang and Leighton Brown, which provides a general computational framework based on the ellipsoid method. So not so practical, but definitely in terms of complexity, the problem is well understood. So they provide a general computational framework for games of what are called polynomial type. What is that? These are games where the number of players and the number of pure actions. So these are games with a finite number of pure actions, where people can randomize over their actions. These actions are basically on simplices. Every person is choosing a randomization, like a point in a simplex, which corresponds to a randomization over deterministic strategies. So for that special class of games, the thing about games of polynomial type, which means that the number of players and deterministic strategies that are available to each player, they're polynomially many in the description, in the coding, in the binary encoding of the game. And the other thing that they want is that given a mixed strategy for each player, so given x1 in the simplex, x2 in the simplex, and so on and so forth, there is a polynomial time algorithm, polynomial in the description of the game and the description of the mixed strategies, that can compute the expected payoff of every player. So their claim is that if you have any game with these two properties, polynomially many players and pure deterministic strategies per player, and a polynomial time algorithm that computes expected payoffs for product measures of mixed strategies, then there is a generic algorithm called ellipsoid without hope that computes correlated equilibrium. The interesting thing is that if you think about it, a correlated equilibrium is a joint distribution over deterministic strategies for the players. So correlated equilibrium, the object that you're trying to compute, lives in a very high dimensional space, potential exponential in the description of the game. So what ellipsoid without hope does here is to identify a low description complexity correlated equilibrium. It doesn't just compute a correlated equilibrium, which could be, as I said, an exponentially large object. Right, you have polynomially many players with polynomially many strategies each in the description of the game. So the joint strategy profiles are number of actions to the number of players, right? So these are exponentially many. However, the method identifies a low complexity one. So that's pretty cool that it does. Here's an example of games that are of polynomial type. These are graphical games. So these are games where players are nodes of a network, say a sparse network. And a player's utility depends only on the strategies of the players that he interacts with. So that's a game where, you know, the number of players is as many as the number of nodes in the network. Every node has a finite number of deterministic strategies, and you can easily compute expected utilities for a product measure of strategies. So that's a good example of these types of polynomial type games. An example of games that are not of polynomial type are extensive form games, which is the game theoretic model of turn-based games like poker and Go and chess, right? Because here, I mean, it depends on how you describe the game, I guess. But yeah, even if you lay out the whole game tree, the number of deterministic pure strategies are exponentially many in the size of the tree. Stochastic games, which is a game theoretic model of multi-agent RL, is another example where the total number of deterministic policies is exponential in the description of the game. So these are not games that can be handled by this method, but a lot of other games that are useful and interesting can be handled by this method. So that's an interesting method to have in mind when you think about correlation in multiplayer games. Yeah.
One quick question. I understand that polytype games is somehow the way that the theorist will describe a general kind of game.
Yeah.
Out of curiosity, I see why someone would try to use the ellipsoid like the TCS version of gradient for the two players.
Right.
Does anyone try to implement something like interior point method in order to achieve better rates in that kind of stuff?
Yes, I want to discuss this next. But so people have not. Okay, so I don't know. I do not know how to implement the interior point method for that. But of course I know, and that's what I'm going to discuss in the next slide. Algorithms based on monitored learning. These are not polynomial in the TCS way, but these are efficient methods to compute equilibrium or correlate equilibrium in these games. And the question was, I guess, yeah, okay, implied by my answer. Yes.
So there may be a whole set of course correlated equilibrium.
Yes.
Can you target a specific one? Or?
Not with this method. Yeah, you can maybe optimize certain objectives, but not. You cannot optimize any, as general objectives as you can when the game is a two-player game, which it's an easier problem in this family. Yeah. Yeah. 5 minutes. Okay. In terms of more practical algorithms, so this is an ellipsoid with a hole. It's used the ellipsoid method in a very interesting way. It runs the ellipsoid in the dual of the problem, so it considers the dual of the correlated equilibrium computation problem, which is trying to compute an exponentially big object. Considers the dual. The way it's the primary setup, the dual is invisible. It runs the ellipsoid on an infeasible problem. So the ellipsoid is going to prove that the dual is infeasible. And the hyperplanes that the ellipsoid uses to show that the dual is infeasible are used to zoom into a low complexity correlated equilibrium for the primal. Okay, roughly speaking, this is the idea. But it does use the ellipsoid algorithm. It is not so practical. So how about practical algorithms? Well, a generic way, as I was saying earlier, to converge to correlated or to coarse correlated equilibrium is by doing no-regret learning, such as so have every player run by themselves their own no-regret learning algorithm, such as online gradient descent, multiplicative weights update, follow the regularized leader, follow the perturb leader, and so on and so forth. In fact, this no-regret learning is used in recent successes in the practice of solving difficult games. Like it is used in the heart of the Libratus algorithm that beats humans in poker. Now, what do we know about no-regret learning in multiplayer games? We know that if agents interact over T rounds, then each of them experiences a regret that scales like root T for not having fixed action in hindsight, which effectively equivalently reflects a rate of convergence to coarse correlated equilibrium that goes down like 1/√t. And the question is, how much can you push this rate of convergence? The obvious bound, upper bound on the regret in a game setting is constant. Which means that the obvious lower bound in the rate at which the empirical play converges to correlated equilibrium is 1/t. So there's a gap between what we know, which is 1/√t, and what the obvious lower bound is, which is 1/t. So the question is, can you get this 1/t? Right? So as it turns out, this negative momentum methods that I was talking about in the beginning of this hour are very useful to get closer to the obvious lower bound in the bounds how much the regret should grow. So there's a line of work that one celebrated paper by Vasilis and company showing, for example, that in general games, if you use a negative momentum method, rather than √t regret, you can get it down to t to the quarter. Okay, so you can improve on the obvious one that you get for against adversaries. So in a game context, so opponents are not like adversaries. Okay, that's the meaning of this slide. So this is tight if you play against adversaries, but if you play against players who are trying to optimize their own utilities, you can beat this √t and get a t to the 1/4 if you use one of these optimistic gradient methods or related methods. In fact, some more recent line of work showed that in two-player games, you can even get t to the 1/6. While some old work that we had shown that in two-player games, okay, much more specialized class of games, you can even get down to polylog t. So the question is, like, where is the answer? Okay, what's the best? How much can you push this technology? So a very recent, work of my own shows that actually you can get polylog t in general sum games. So in arbitrary games, you can come up with methods, and these are, methods like optimistic gradient descent ascent, whose regret scales like polylog t over t rounds of interaction, which means that you have near optimal convergence to correlated equilibrium. So in this work, we saw coarse correlated equilibrium, but in some follow-up paper, we also show that for correlated equilibrium. So I don't have too much time to talk about this proof. It is on the slides that are shared, but let me give you the idea in 2 points. The idea is this, that when all players use negative momentum, like optimistic gradient descent, then the loss sequence that an agent is experiencing is smooth. Not only is it smooth, so not only the loss functions that the player experiences change slowly, but something more than that. They're higher order smooth. So they're really, really smooth. Okay. And against really, really, really smooth sequences of losses, negative momentum does a great job in minimizing regret. So this is roughly speaking the intuition. Okay, so let me say it another way. So what's happening here is this, that in a game setting, everybody's using their own variation of so their own learning algorithm. Now, that learning algorithm depends on the past experience of the player. And like in one step, that experience doesn't change very fast. Okay, so what they're going to do in the next round is close to what they were doing in this round, and close to what they were doing in the previous round, and so on and so forth. And if you add to that, rather than a standard no-regret learning algorithm, you have them use this optimistic variance, they're even, smoother. The sequences of actions of the player are even smoother, which means that their opponents are also facing really, really smooth opponents. And it's such a smoothly changing environment. Optimistic methods are really good to get you to get the regret to go down. This is roughly speaking the intuition. And I think I should wrap it up here with concave games. And I don't know if there are further questions, but thank you very much. Mike.
So it's a beautiful result, first of all. Very nice.
Thank you.
When I think of very, very smooth in optimization, I don't think of negative momentum. I think of momentum. I think of Nesterov
Right.
and so on.
Yes.
And so I wondered if this result really depends on the negative, look ahead kind of momentum
It does.
critically, or is it also the case that a Nesterov style for
No.
each agent would work, or you've actually shown that it doesn't?
No, with
So why is the smoothness so a negative going again?
right. So that's a great question. So remember, recall my picture from earlier, right? Where gradient descent dynamics spiral around and away from the equilibrium. If you add positive momentum to that, you're going to be spiraling away even faster. So inherently, the momentum is wrong. So you don't want to, momentum. You want to fight the momentum as opposed to, follow the momentum. So that is what's going on pictorially. I mean, so it does critically depend on, predicting. It's ultimately, I mean, okay, here's the slide. So multiplicative weights update. So here we're in a game context. So we have to stay in the simplex. So a nice way to stay in the simplex is to do multiplicative updates. What is multiplicative updates? In every round, player I at round T, player I assigns to action A the same probability that we're assigning before, with an exponential penalty with respect to the loss that this action experienced in the last round, in the current round. This is optimistic. This is multiplicative weights update. The optimistic version is exactly the same code, except you do this prediction that I was doing earlier. Like you predict the future loss that this action will experience with this, doubly counting the most recent round and subtracting the previous round. So you're anticipating what's going to happen in the next round, and this is very critical to prove this. Yeah. So in particular, if you do, for example, multiplicative weights update, you can, Chen and Peng showed that you cannot improve the root T. Like this root T is inherent there, and to improve it, you have to, so you have to do that.
More on the details of that. So the intuition that stable and optimistic, it was there for the two quarter. The improvement comes from using the higher order.
Correct. Yes. I mean, okay. So. No, but I want to answer specifically to Vasilis because the starting point is his analysis. So Vasilis showed that, and company, showed that the regret that a player experiences in T rounds depends on he has a different formula, but this is related, on how fast, how much the loss is, the distance traveled by the loss sequence, which is this, effectively this. Now, in this upper bound, there is this other term, which is the losses. So in the previous analysis, this term was ignored. And if you only use that, you can still improve the rates. Okay, but now what you want to argue is that effectively you can kill this if you actually look in the info in here. All right, and that necessitates you to at least it necessitates to consider higher order smoothness, because kind of like in higher order you can easily establish that this distance traveled is very small, and then you percolate that down to the zero level, roughly speaking. Okay. Yes. Oh. Yes.
Probably this is a question of people that they love FTRL.
Yes.
But I'm asking it also because Mike asked about different kind of algorithms that can achieve that. Did you ever try to apply any other optimistic version of an FTRL to see if this regret is similar? I want to understand if, for example, the negative entropic regularizer that gives the multiplicative weight update finally is a critical point to take this logarithmic regret.
Okay, yeah. So I guess that's a great question, first of all, and I should say that in Vasilis's result, you don't need to use specifically optimistic heads. You can use any method that that has negative momentum in a particular sense, And for example, like if you do FTRL, follow the regularized leader, if you do any optimistic follow the regularized leader method under some mild conditions, you can get this improvement. Okay. Now for our proof, we currently critically use the functional form because sort of like when we analyze higher order smoothness of the loss sequence, we like the fact that we have this softmax function here. Like this softmax function is very nice. So we use that to prove higher order smoothness for our dynamics. But that being said, I believe that you can extend this to more general methods. So that's an interesting open question. So yeah. So I believe you can extend this to more general FTRL, optimistic of the FTRL methods. Yeah.
One last question.
Yeah.
So I have two questions.
Yeah.
The first one is about the analysis. Okay, so if you, instead of optimistic, you do like higher order, can you kill the log to the fifth?
Oh, higher order, you mean?
Higher order differences in your
like in my prediction.
in your prediction look like yesterday, 2 days ago, 3 days ago, etc.
2 minus 3, 2
Yeah,
minus 4.
exactly. If you can kill the log to the fifth, have like 1/t eventually.
Right, with like better predictions. Not
Right.
that I know. Not that I know, but I don't know. Max is here in the audience. Maybe he knows.
Okay.
And Max is the co-author of this paper. Official son.
So the other question I think it's also for Vasilis for the RVU type bound. If you have last iterate, you might have speed up in the regret. So like have faster average iterate.
No, as I was saying earlier, commenting on a line of work with Noah Golovich, we know that the rates for last iterate, at least for these two methods, right? So like optimistic gradient descent ascent and extra gradient, must be slower.
So last iterate is slower than average iterate. All I'm saying is that if last iterate, the fact that you have last iterate can give you information about faster average iterate.
Oh, I see.
I mean, if you see your lemma 1, the right-hand side, right? Say that you know that the trajectories are really, really small, right? So you will have small regret in some sense. So say that I know that you have last iterate, like optimistic.
Yeah.
Maybe this is a reason why, I mean, in high level or conceptually, that you have low regret because you have last iterate conversion.
Yeah, conceptually, this is, this is what is, taking place in the background. Like one interesting question is, can you derive, for example, last iterate, for another question, a bit orthogonal to yours, but can you derive last iterate from this equation? That's another interesting question.
Yeah.
I don't know how to derive, but I haven't thought about it too much. But yeah, like intuitively, this is very well what could be taking place. Sure, but you can write it for 2 players as well, right? Yeah, okay, sure.
So let's take the rest of the discussion offline. So we're going to have a 2-hour break for lunch, and then Eva Tauber is going to be speaking virtually. She's going to be looking about general sum games and qualitative equilibrium and learning as a solution concept. We'll all be here. It's going to be shown here. You can either join here or join, virtually too. But yeah, we're all going to be here, and there's going to be session. Thank you.